In this session, you will learn about different types of feedback topologies applied to amplifiers. Based on the quantity to be amplified, that is either voltage or current, and on the expected form of output, amplifiers are classified into four categories: voltage amplifiers, current amplifiers, transconductance amplifiers, transresistance amplifiers. Let us discuss about each classification in detail and determine which feedback topology is suitable for each case. Voltage amplifiers. Voltage amplifiers are intended to amplify an input voltage signal and provide an output voltage signal. As the output quantity is voltage, the feedback network samples the output voltage, and the feedback signal XF is also voltage, which is mixed with the source voltage in series. The most suitable feedback topology for this amplifier is voltage mixing, voltage sampling. Because of the series connection at the input and shunt connection at the output, this feedback topology is also known as Series-Shunt Feedback. An example of Series-Shunt Feedback is a two-stage MOSFET amplifier shown here. You can observe that the output voltage is sampled of the second stage transistor is sampled by a voltage divider network, which is a feedback network, and the voltage we drop across the resistor R1 is fed to the source of the MOSFET. So Vi equal to Vs minus Vf. So thus the feedback is negative or degenerative. Current amplifiers. In current amplifiers, the input signal is a current. Then it is represented by a Norton's equivalent circuit here at the input. The output quantity is also current. The feedback network sample the output current just as an ammeter measuring the current, that is in series. The feedback signal XF is also a current, so that is IF. This is mixed in shunt with the source current IS. So that's the feedback topology that is most suitable for this current amplifier is current mixing, current sampling topology. Because of the shunt connection at the input and the series connection at the output, this feedback topology is also known as Shunt-Series Feedback. As an example of Shunt-Series Feedback, two-stage amplifier is shown here, where the current output current of the second stage is sampled here, where the sample network is RF and RM, which is again a resistive network. And looking at the current directions over here, we can write IA equal to IS minus IF. So thus the feedback is negative. In transconductance amplifiers, the input signal is a voltage and the output signal is a current. The gain of the amplifier is given by output current by input voltage, which is conductance, hence the name transconductance amplifiers. The feedback network samples the output current, and the feedback signal XF is a voltage here, which is mixed in series with the source voltage Vs. Now, the feedback topology suitable for this amplifier is voltage mixing, current sampling topology. Due to series connection at both input and output, the feedback topology is also known as series feedback. As an example of transconductance amplifier, you can see a two-stage amplifier here, where the output current I0 is sampled here with using a feedback network RF, which is a resistive network. The drop across this resistor RF is fed to the source terminal of the MOSFET Q1. So Vi can be written as Vs minus Vf. In a way, this is a negative feedback. In transresistance amplifiers, the input signal is current and the output signal is voltage. The gain of the amplifier is given by output voltage by input current, which is resistance, hence the name Transresistance Amplifier. The appropriate feedback topology is current mixing voltage sampling type, and due to shunt connection at both input and output, the feedback topology is also known as Shunt-Shunt Feedback. This is an example of a feedback transresistance amplifier where the output voltage is sampled by the feedback resistor RF, and it is the feedback signal XF, which is a current, is mixed with the base terminal of the transistor. Now, observing the current directions at the input of the transistor, you can write input current II equal to the source current minus feedback current. Thus, the feedback is negative or degenerative. In the next session, let us analyze all the four feedback topologies for closed loop gain, input resistance, and output resistance. First, let us start with Series-Shunt Feedback Amplifier. The ideal structure of Series-Shunt Feedback Amplifier with basic amplifier and feedback network replaced by its equivalent circuit is shown like this. It consists of an open loop amplifier and an ideal voltage mixing and voltage sampling feedback network. The voltage gain of a basic voltage amplifier is given as A equal to V naught divided by Vi, where V naught is the output voltage of the basic amplifier and Vi is the input to the basic amplifier. The circuit has an input resistance Ri and an output resistance R0. Assume the source resistance and the load resistance are included inside the basic amplifier. Beta is a feedback factor, and connecting the beta circuit does not affect or change the value of the open loop gain A, so that the beta circuit does not load the basic amplifier circuit. Now, the input to the amplifier is given by Vi equal to Vs minus Vf, as this is a negative feedback. The feedback voltage Vf is equal to feedback factor beta times the output voltage. Now, the closed loop voltage gain of the amplifier is given by output voltage by source voltage, that is V0 divided by Vs. We can write that the source voltage Vs to be equal to Vi plus Vf from the previous expression. On substituting the values of feedback voltage or the feedback signal, we can replace Vf by beta into V0, and subsequently V0 replaced by A into Vi, we end up with Vi into 1 plus A into beta. Now, substituting these values in the closed loop voltage gain, so A will be equal to V0 by Vs, that is equal to A into Vi by Vi into 1 plus A into beta. So on cancelling Vi, you end up with A divided by 1 plus A into beta, which is exactly equal to the negative feedback overall voltage gain. Let us find the input resistance of feedback amplifier. Let Ri be the input resistance of the basic amplifier and Rif be the input resistance of the closed loop amplifier. So the input resistance with feedback amplifier is given by Vs, that is source voltage, by input current. So input current I can be expressed as it is Vi divided by Ri, the input resistance to the basic amplifier. So we know the value of Vs. So on substituting the value of the source voltage obtained from the earlier slide, so on substituting this, we'll end up with an expression Rif is equal to Ri into 1 plus A into beta. So this indicates that the negative feedback increases the input resistance by a factor equal to amount of feedback. To find the output resistance of the feedback amplifier, reduce the source voltage to 0 and apply a test voltage at the output. Due to this test voltage, the current in the circuit is taken as I. Now, from the circuit, we can define that output resistance is equal to the test voltage by the current in the circuit. Now, from figure, we can express the test voltage as I into R0 plus A into Vi. And from this, the current can be obtained as I equal to Vt minus A into Vi into R0. Since Vs is equal to 0 here, Vi can be written as minus Vf, that is equal to minus beta into V0, that is equal to minus beta Vt, as V0 is equal to Vt in this circuit. So now the previous current expression can be written as I equal to Vt minus, on replacing the value of Vi here, you will get A into beta into Vt divided by R0. So substituting all these values in the output resistance expression, we get R0f equal to R0 divided by 1 plus A into beta. So from this, it is evident that the negative feedback reduces the output resistance by a factor equal to amount of feedback. To summarize, the closed loop voltage gain of feedback amplifier is given by AF equal to A divided by 1 plus A beta, and the input resistance of feedback amplifier including the source resistance is given by RIF is equal to RI into 1 plus A beta, whereas output resistance of series shunt feedback amplifier is given by R0F equal to R0 divided by 1 plus A into beta. Next, let us discuss about series feedback amplifier. The series feedback topology is best suited for transconductance amplifiers. The ideal structure of series feedback amplifier consists of an open loop amplifier and an ideal feedback network. The open loop amplifier has an input resistance Ri and an output resistance R0. The short circuit transconductance is given by A equal to output current by input voltage. The feedback network samples the short circuit current I0 and provides a feedback voltage Vf. So that is Vf is equal to beta into I0. Thus, Vs is Vf is subtracted from Vs, so Va can be written as Vs minus Vf. So thus the feedback is negative. Here, A is a transconductance and beta is a transresistance, and A into beta is a dimensionless quantity. So the source and the load resistance are included in the basic amplifier circuit itself. The closed loop gain of the feedback amplifier is given by the output current by the source voltage Vs. Now Vs, we can write it as Vi plus Vf from the previous expression, this expression. So from this, on replacing the value of the feedback signal Vf, we can end up with Vs is equal to Vi into 1 plus A into beta. On substituting this in the closed loop gain expression, AF will be equal to A into, on simplifying this, we will end up with an expression that is AF equal to A into 1 plus A divided by 1 plus A into beta. So the gain, closed loop gain is less than the basic amplifier gain A, or the open loop gain A. The input resistance with feedback RIF is given by the source voltage by the input current. So on substituting the values of Vs, we'll end up with an expression RIF is equal to Ri into 1 plus A into beta. So this we have discussed in the previous topology also. So because of the series mixing, the input resistance with feedback RIF will be larger than the input resistance of basic amplifier by a factor equal to the amount of feedback, that is 1 plus A into beta. So now let us consider how to find the output resistance of the feedback transconductance amplifier. To find the output resistance, reduce the source voltage Vs to be equal to 0 and apply a test current It at the output. Then the output resistance of the feedback amplifier is given by the output voltage by output current. So that is V divided by I into IT. So from the circuit diagram, we can write the output P equal to the drop across the resistor R0 and the drop across the current source. So it's A into Vi into the output resistance R0. So this can be written as I, the test current, minus A into Vi into R0. We know that since the source voltage is 0 here, Vi can be written as minus Vf, that is equal to minus beta into I0. So that is equal to minus beta into the test current that is applied here. So on substituting the values for Vi, we'll end up with R0 of equal to this expression. So on simplifying, we get R0 f is equal to 1 plus A into beta into R0. So the negative feedback thus increases the output resistance in series feedback amplifier by an amount equal to an amount of feedback 1 plus A into beta. To summarize, the series feedback topology increases both input and output resistance of the amplifier. Next, let us discuss about shunt feedback configuration. In shunt feedback amplifier, the basic amplifier has a trans resistance A equal to V0, that is output voltage by input current. So the feedback signal is given by IF equal to beta into V0. Hence beta is called as transconductance. Now the input current is written as the source current minus the feedback current IF. So the closed loop gain is given by output voltage by the source current. The source current can be written as input current to the basic amplifier plus the feedback current. So on substituting the values of IF and simplifying, we get the source current to be equal to II into 1 plus A into beta. On substituting this in the closed loop gain of feedback amplifier, we'll end up with an expression AF equal to A divided by 1 plus A into beta. So this shows that the feedback provided here is a negative feedback. The input resistance with feedback is given by input voltage Vi divided by the source current Is. So on substituting the values of Is from the previous slide, we'll end up with an input resistance of feedback amplifier as Rif equal to Ri divided by 1 plus A into beta. So thus the shunt connection at input results in reduced input resistance. We know that for shunt connection at the output results in reduced output resistance. So the output resistance of a feedback amplifier with the shunt feedback topology is given by R0f equal to R0 divided by 1 plus A into beta. So to summarize, shunt feedback topology decreases both input resistance and output resistance of the amplifier. The next configuration for discussion is shunt series configuration. The shunt series feedback topology is best suited for current amplifiers. So the basic amplifier here is current amplifier and the gain is given by output current by input current. The feedback signal, the sampled signal is current and the mixed signal is also current. So the feedback signal IF is equal to beta into I0. Now the input to the basic amplifier II can be written as the source current minus the feedback signal IF. So therefore II equal to IS minus IF. Now the closed loop gain of the amplifier is given by the output current by the source current. So the source current can be written as the input current plus the feedback signal IF. So on replacing the feedback signal IF by beta into I0 and further with beta into I naught, and further with A into II will result in an expression AF equal to A divided by 1 plus A into beta, which says that the feedback employed here is negative. The input resistance with feedback is the resistance seen by the current source Is. So RIF equal to input voltage by the source current Is. So on substituting the values of value for expression for the source current, we'll end up with the input resistance as RIF equal to Ri divided by 1 plus A into beta. So this shows that the input resistance with feedback is less than the input resistance of basic amplifier by a factor equal to amount of feedback. We know that for series connection at output results in increased output resistance. So therefore R naught F is given by R naught into 1 plus A into beta. So the output resistance is increased by a factor equal to the amount of feedback. To summarize, the shunt series feedback topology decreases the input resistance and increases the output resistance of the amplifier. So the effect of feedback on input and output resistance for all the 4 different topologies is shown here. Series shunt topology, which is applicable for voltage amplifiers, the input resistance is increased and the output resistance is decreased. And for series topology, which is applicable for or more appropriate for transconductance amplifier, both the input resistance and output resistance are increased. Whereas for shunt topology, which is much suitable for transresistance amplifiers, both the input resistance and output resistance of the amplifier are decreased or reduced. In shunt series topology is much suited for current amplifiers, where the input resistance is decreased and the output resistance is increased for the feedback amplifier. Thank you.